Hello everyone! In this video, you will learn the second section of Chapter 6, which is about ripping. What do you see in this picture? It is a dozer that is ripping rock. In previous chapter, you learned that a dozer can be equipped with a rear ripper. Let's watch a short clip about how dozer is used for ripping. The single objective of this lesson is to estimate the production of dozer when it is used as a ripper. In the previous section of this chapter, you learned that we can use blasting to excavate rock. So, when to use ripping or blasting? This decision is typically based on cost. Ripping rock and hauling with scrapers can sometimes provide cost savings as much as 50% over the alternative of drilling, blasting, loading with loaders, and hauling with trucks. Ripping also has fewer safety hazards and lower insurance costs than drilling and blasting. So, when to use ripping to excavate rock? Caterpillar has another performance handbook specifically for ripping. This handbook provides a list of physical characteristics that favor ripping rather than blasting, including the following. Number 1. Use ripping when the rock bench has frequent planes of weakness, such as fractures, faults, and laminations. Number 2. It is best to use ripping for rocks that are broken into small pieces due to weather condition. Rocks typically expand and contract when the temperature changes. Since rocks are composed of various minerals, which expand and contract at different rates, this causes cracks and gradually breaking down the rock. Number 3. Rocks with high moisture permeated formations are also easy to rip. Number 4. Rocks with a high degree of stratification, which means rock that is formed from multiple layers. Number 5. Rocks with high brittleness. This type of rock is fragile and can be easily destroyed. Number 6. Rocks with low strength. And finally, use ripping for rocks with a low seismic velocity. Those rocks are light and have a low density. Sedimentary rocks can be excavated using the ripping method. Examples of sedimentary rocks are sandstone, limestone, or shale. These types of rocks are highly stratified, which is composed of multiple layers. Thus, they are most easily ripped. Rocks that do not have those characteristics mentioned earlier will make ripping more difficult. Massive rocks such as granite, marble are hard to rip. Other characteristics that unfavor ripping include rocks without planes of weakness, crystalline rock, non-brittle rock, energy-absorbing rock fabrics, and rocks with high strengths or high field seismic velocity. Igneous rocks are not suitable for ripping. These rocks are rarely stratified, thus most difficult to rip. Examples of igneous rocks include granite, basalt, and diorite. Section 2. Seismic wave velocity. The rippability of rock is typically measured by the seismic wave velocity of the material, which can be calculated using charts. Various performance charts have been developed by field tests on a variety of materials. You can see figure 6.17, page 105, in your textbook for an example of seismic wave velocity charts. This is figure 6.17. This chart gives you the velocity range for various types of rock. It also indicates if a certain type of rock is rippable or not. For example, the seismic wave velocity of granite varies from 3,000 feet per second to 12,000 feet per second. Ripping can only apply for soft granite, which has a velocity below 7,000 feet per second. Considering the extreme variations among materials, and even among rocks of a specific classification, the charts must be recognized as being at best only by one indicator. Caterpillar Performance Handbook is another source to find rippability, based on seismic wave velocity. The figure shown in the next page is the performance chart for CE4390 dozers. This is the performance chart provided by Caterpillar. It has the same format as the figure 6.17 in your textbook, but it may give you a different estimated seismic velocity range. Please note that ripping is still more art than science, and much will depend upon operators' skill and experience. While you should be familiar with the concept of seismic velocity charts, you are not responsible for the material in the text regarding the use of seismic waves to determine layer velocities and depths. Section 3. Ripping production. The ripping production depends upon the following factors. Number 1. Tractor speed, or how fast the dozer can go. Number 2. Shank depth. And number 3. Number of shanks, which determines the width of the ripped area in each pass. To calculate the tractor speed for ripping, you need to find the maximum drawbar pull using the performance chart when it is in the first gear. Generally, the tractor speed is ranging from 1 to 1.5 miles per hour. Shank depth is the maximum depth that the shank penetrates into the rock surface. This is dependent upon the characteristics of the rock and the machine. If possible, you should rip to a uniform depth. This is very important when scrapers are being used to haul the material. When the rip depth is uniform, you can minimize idle time for scrapers. The shank depth is typically low at the start of a pass. Then you need to gradually penetrate the shank deeper into the rock until a desired depth is achieved, and remain it during the pass. Number of shanks is another important factor that determines the ripping production. Rippers may have 1, 2, 3 or even more shanks. Number of shanks depends upon the size of the dozer, the depth of penetration desired, the resistance of the material, and the degree of breakage required. Here is a ripper with 2 shanks. This one has 3 shanks. It can have up to 5 shanks. Section E. Estimating ripper production. There are several methods to estimate ripping production. Quick method is one popular approach. Using this method, you need to do several field experiments over a certain measured distance using your machine. Then, you determine the average cycle time, including turnaround time at the end of each pass. Once you got the cycle time from the field tests, now you can estimate the volume of rock being ripped using the length, width, and depth of the ripped area. Ripping production can be estimated using equation 6.6 in your textbook, as shown here. In this equation, production is measured in bank cubic yards per hour. D is the average penetration depth in feet. W is the average width of the ripped area in feet. L is the length of each pass in feet. E is the job efficiency factor. T is the time for one pass, including turn times, in minutes. 2.22 is the unit conversion factor. I will explain how we got this factor in the next slide. In this equation, D is in feet, W and L also in feet. E has no unit. Time T is in minute. Without the 2.22 factor, this equation gives you the production in cubic feet per minute. To convert it into cubic yards per hour, you need to multiply it by 60 minutes per hour and divide it by 27 cubic feet per cubic yard. If you do the math, 60 divided by 27, you got 2.22. That is why you got this factor in the equation. Experience has shown that the Caterpillar Performance Handbook also states that the results from this quick method are usually 10 to 20% higher than the actual production that can be expected on the job. Again, since your textbook does not make this adjustment, we will not use any adjustment factor in this class, so do not divide the result from equation 6.6 by 1.2. Another method for estimating ripping production is use the seismic velocity charts. For this method, we will use the performance charts in the Caterpillar Handbook. You can find the charts in page 1981 of the handbook. These charts are typically based on ideal requirements with various assumptions. You can find the details of those assumptions in page 1981 in the handbook. The production rates from the charts require a great deal of judgment to adjust the results to reflect the field conditions for a specific project. This slide lists the assumptions used by Caterpillar when they developing the chart for estimating ideal ripping production. For example, they have the following note for ripping igneous rock, which says an igneous rock with seismic velocity of 8,000 feet per second or higher for the D11T and 6,000 feet per second or higher for some models. The production figures shown in the chart should be reduced by 25%. The bottom line is, you must read carefully any assumptions and considerations when using the performance charts. Here is the chart for the model D9R with a single shank. The horizontal axis indicates the seismic velocity in thousands feet per second. The left vertical axis shows the production in bank cubic yards in 1 hour. If you need to find the production in bank cubic meters per hour, you need to use the right vertical axis. On this chart, you can see two different curves. A is for the maximum production in the ideal condition. B is the minimum production when operating in an adverse condition. Typically, the ripping production will fall in the gray area between these two curves. Suppose that the seismic velocity is 4,000 feet per second. The ripping production, if using D9R or D90 dozer with single shank, will be between 850 to 1,850 bank cubic yards in 1 hour. For the same velocity, if using D11T with single shank, you got a much higher production. It would be between 1,250 to 2,900 cubic yards. Now, let's do a quick example. How many D90 dozers are needed to rip 8,000 BCY of trap rock in 8 hours? The rock has a seismic velocity of 6,000 feet per second. The conditions should be considered average. Efficiency will be a 45-minute working hour. Step number 1. You need to determine whether the material is rippable or not. To answer that question, you use the chart in page 1977 in the handbook. The material is trap rock at 6,000 feet per second. It is in the black area. It means the material is rippable. Step 2. Get the ideal production from the chart. Remember, the problem says average conditions. This is the performance chart for D90 dozers from the Performance Handbook. With the velocity of 6,000 feet per second, the maximum production rate would be about 1,000 cubic yards. The minimum would be the 250 cubic yards, corresponding to the bottom edge of the gray area. Since the condition is average, let's use 500 bank cubic yards per hour. Step 3. You need to check the assumptions in the handbook to see if you need to reduce the production. As noted in page 1981 in the handbook, igneous rock with seismic velocity of 8,000 feet per second or higher for the D11T and 6,000 feet per second or higher for some models including D9T. The production figures shown in the chart should be reduced by 25%. In this example, our material is trap rock, which is an igneous rock, and your velocity is 6,000 feet per second. So you need to reduce the production by 25%. The efficiency is 45 minutes per hour, as given in the problem. Now, you can calculate the production. It is equal to production of 500 BCY per hour, multiplied by 0.75, since you need to reduce the production by 25%, and then the efficiency factor, 45 per 60 minute. Finally, you got 281.25 BCY per hour. Let's say the estimated production is 280 BCY per hour. Step 4. Determine the number of dozers. What you need to do is simply divide the total rock volume to be ripped, 8,000 BCY, by the total production that each dozer makes in 8 hours, which is equal 8 hours per dozer, times hourly production 280 BCY, or 3.6 dozers. Let's round it up to 4 dozers. Heavy ripping is hard work. Machines used regularly in ripping operations should have their owning and operating costs increased by as much as 30–40%. Section 4. Estimating rock excavation production and cost. Since the blasting section is no longer covered in this course, Part A of Section 4 is not required. You can read the example 6.4 for your own information. No homework or test problems on blasting cost will be given. Part B, Estimating Cost for Ripping Production. I will explain the process using example 6.5, page 106 in the textbook. In this example, you are required to estimate the hourly production and the unit cost of rock excavation by ripping for the problem of example 6.4. Field tests indicate that a D7G dozer with ripper can obtain satisfactory rock fracturing to a depth of 27 inches with 2 passes of a single ripper shank at 3 feet intervals. Average speed, including turns, is estimated at 82 feet per minute. Let's review what are given. A single shank ripper. The speed is 82 feet per minute. The ripping depth is 27 inches. The interval is 3 feet, which is width of each rip path. Due to the rock properties, 2 passes are required for each rip path to achieve satisfactory rock fracturing. Here is the cost information given. Labor cost, or the operator cost, is $20 per hour. The equipment cost, including O&O cost, is $75 per hour. For production, You use equation 66, as shown here. From the problem, the depth is 27 inches, or 2.25 feet. The width of each ripped area is equal to the interval, 3 feet. The length of each pass is L. It is not given, so just keep L there. The efficiency is 50 per 60 minutes. In the denominator, the total time T is equal to total length, L divided by the speed, which is given as 82 feet minute. Also, since you need to do double ripping as required in the problem, you need to divide everything by 2 passes. Calculate this, you got 512 BCY per hour. The unit cost is equal to sum of hourly labor cost and equipment cost, $95 per hour, divided by the hourly production 512 BCY per hour. We got $0.186 per BCY. This is the end of this video. Please complete all homework problems except for the first one, which has been canceled. Goodbye for now, and see you next time.